Hey guys, welcome back to our YouTube channel. Now this video is part of our linear algebra for data science video series. This is part 2 of eigenvectors and eigenvalues concept. Okay, now in the last video, we have learned about the two basic concepts. When I multiply a vector with a matrix, I am going to perform two things. So what are those two things? One is scaling and the another one is called as rotation. So this is how my vector will be transformed as a result of multiplying my matrix. Okay, now this is what we have seen in our last video. Now let's continue our learning. Now observe this thing, guys. So here if you see the diagram, so this is called as a vector field. Now here in this vector field, I have various vectors. So you can clearly see that I have vectors pointing in multiple directions. Now for the better intuition, let's say I have a vector field, okay, and this vector field contains some vectors like this. Okay, now for the benefit of it, let's assume that I'm taking these vectors only, like I'm just writing three vectors, right? Okay, let me write it in a different color. So let's only consider these three vectors that you're seeing over here. Now I'm going to multiply a vector. I'm going to multiply a matrix to this vector field. Now as a result of multiplying the matrix for this vector field, what it does is it again does the same thing to every vectors that will be present in my vector field. Now let's assume I'll be multiplying the matrix which actually scales my vectors. So this would result in scaling this vector, and this would result in scaling this vector, and this would result in scaling this vector as well. So as a result, I have scaled every vector that is present in this vector field. Okay, so do you agree with me on this? Yes. Now moving ahead. Now as we know, so I cannot simply say that, okay, so unless and until I have a diagonal matrix like this, so I cannot have the same effect on every vector in my vector field. Now let's say I'm having a random matrix which has the elements as A, B, C and D. Now if I apply this random matrix on my vector field, obviously it does two things for my vectors. So it does two things. The two things are scaling and rotation. Now when I apply a matrix to my vector field, the vectors which would stay in the same direction, this is very important, guys, the vectors which would stay in the same direction and then it can scale as well, those vectors are called as eigenvectors. Which means that, let's say I'm having a vectors like this, okay, I'm just taking four vectors. So these are four vectors in my vector field. Now when I apply this matrix on these four vectors which are in this vector field, it obviously performs scaling and rotation on each of these vectors. Now as a result of this, let's assume the new vectors are, I'll write the new vectors in blue color. So the new vectors are somewhere like this. Okay, this is new vector and this vector has been transformed to a different direction over here. This is what it has transformed, and this vector has rotated in this manner and this vector has rotated in this manner. Now only one vector which is in the same place but only scaled is this vector. That is my original vector over here. So if I use my highlight, so this is that particular vector. Now the vector which has just performed the scaling and it stayed in the same direction, so this kind of vector is called as eigenvector. So eigenvector is a vector which stays in the same place and which does not change the direction even when I multiply a matrix on top of it. And the scale by which the vectors will be scaled, that scale is called as a eigenvalue. Now let's assume if I have increased the scale by 2, that means if the coordinates were 2, 4, and as a result of this transformation, the new coordinates is 4, 8. That means I have scaled my original vector 2 times. So the eigenvalue will be equal to 2. So this is the intuition behind eigenvector and the eigenvalue. when I apply a matrix on my vector field, the scale in which my eigenvectors will get changed, so that scale is called as eigenvalue, and eigenvectors are the vectors which doesn't change their direction when I apply a transformation on it. Okay, so this transformation is done with the help of a matrix. So this is the intuition behind eigenvectors and eigenvalue. I hope you can now correlate as why the concept of scaling and rotation is important to understand this concept of eigenvectors and eigenvalues. Okay, so now that we have the theoretical understanding of this eigenvectors and eigenvalues, let's see how we can find the eigenvector and the eigenvalue for a given input matrix. So here we have written as eigenvectors are widely used in machine learning libraries. So intuitively, given linear transformation represented by a matrix A. So I hope you can now think back as why we are talking about linear transformation, because when I talk about transformation, it does two things: rotation and scaling. Okay, so given linear transformation represented by a matrix A, eigenvectors are the vectors that when the transformation is applied, change only in scale, not in direction. More formally, this is given by A into V is equal to lambda V, where A is a square matrix, lambda contains the eigenvalues, and the V represents my eigenvectors. Now, in order to find the eigenvalues and the eigenvectors, we can make use of EIG, which is present inside by NumPy library. Alright guys, now observe the definition. This concept is very important and it is one of the common interview questions, guys. What is eigenvector and what is an eigenvalue? So eigenvectors are the vectors which doesn't change in direction but only changes in scale when a linear transformation is applied on it. That means when I multiply a matrix over my vector field, eigenvectors are those vectors which changes only in scale and not in direction. And the scale in which it gets changed, those are called as eigenvalues. That's it guys. That's how much simple it is. Okay, now that we have an understanding of this eigenvectors and eigenvalues, let's go ahead and implement it. Here in this cell, I'm just first creating my NumPy array, which contains the values of 2 and 4. So this is the same vector which we have used earlier, guys. First, I'm going to show you how it actually performs scaling. So after that, I'm creating a matrix which has the coordinates as 2, 0, 0, 2, and then I'm multiplying my x and y. As a result of this, this has scaled my input vector by the scale of 2. So my input vector is having the coordinates as 2, 4. Now as a result of transformation, the new coordinates are 4 and 8. And now in the second example, I'm creating my matrix Y, which has the coordinates as 0, -1, 1 and 0. And then I'm taking the matrix multiplication with Y and X. Now as a result of this, obviously, so the new coordinates of my vector is 4, -2. So if I plot it, so if my original vector is like this, then my new vector will be somewhere over here, and this has rotated by 90 degrees. So this is to show that when I apply a matrix on top of my vector, it either performs scaling or the rotation. And sometimes, depending on the matrix values, it can perform both. Alright, now to find the eigenvectors and the eigenvalues, this time I'm creating a square matrix. Okay, now once I create the square matrix, I'm just making use of EIG, which is present inside my linear algebra module, and then specifying my input matrix. So eigenvalues, eigenvectors is equal to np.linearalgebra.eig.matrix. So we have the eigenvalues. The eigenvalues are 14.08, 1.91 and -2. Okay, so these are all my eigenvalues. Now if I display my eigenvectors, so these are all my eigenvectors, guys. Okay, so in this way we can find the eigenvalues and the eigenvectors. Now if I want to connect back using this eigenvectors and eigenvalues, if I want to bring back my original matrix, then we have to apply a mathematical formula, guys. I think the mathematical formula is given by A is equal to Q into L into inverse of Q. So this is the mathematical formula that we'll be using if I want to bring back my original matrix A. Okay, so this is what the formula is. So let me show you how to find this A back. Okay, now this Q is nothing but my eigenvectors. So Q is equal to eigenvectors, and inverse of Q. Obviously, to represent my inverse of Q, I'm going to perform inverse on this eigenvectors. So np dot linear algebra dot inv of Q. Okay, and L is nothing but my eigenvalues. So I'm going to create a diagonal matrix using my eigenvalues. So np dot diag of eigenvalues. The reason I'm converting it to diagonal matrix because I have to make sure that it is mathematically possible to perform Q into L into inverse of Q. Alright, now once it is defined, I'm going to bring back my original matrix A. So I'm going to say A prime, okay, is equal to Q dot L dot R. Okay, and then I'm going to display my A prime. See, my A prime, the values are given by 2, -1, 3, and my original matrix is given by, this is my original matrix. My original matrix is given by 2, -1, 3, 1, 3, 6, 3, 8, 9, and we have generated the same over here using only my eigenvectors and eigenvalues. So this is how I can bring back or generate back my original matrix A using my eigenvectors and eigenvalues. I hope this video has been helpful to you. Like, share and subscribe to our channel for more such updates. I look forward to seeing you in the next class, guys. Till then, take care. Happy learning.